Welcome to The Explainer. Today, we are taking on one of the most famous formulas in all of physics, but we're coming at it from a totally different direction. The entire idea for this comes from Chapter 11 of the book Newton and Relativity by Sestrit, Clementi, and Korf, and their whole approach is just fascinating. They challenge us to build this thing from the ground up.
So how do you add speeds together when you're going, well, ridiculously fast? You might think, easy, you just add them up. But it turns out the universe has a very strict speed limit, and the story of how that rule works is what's so incredible.
And this is it. This is the universe's official rulebook for combining speeds, the thing that makes sure nothing ever breaks that ultimate speed limit. But, the real question isn't just what the formula is, it's how we know it's true.
Now, the traditional way to get to this formula involves some pretty heavy concepts, like Lorentz transformations and Einstein's big idea that the speed of light is the same for everybody. But what if I told you we don't need any of that? What if the answer was hiding in plain sight all along, inside some of the oldest, most fundamental laws of physics?
All right, so here's our game plan for today. We're going to start with a clever thought experiment. Then, we'll run a quick test drive with old-school classical physics just to make sure our method is solid. And then, we're going to unleash that same method on the full-blown relativistic problem and see what happens.
So we're really going against the grain here. And it's so important to understand this one thing about our source material. The relativistic formulas we're about to use for energy and momentum, well, they were also derived in the earlier chapters of the book without ever using Einstein's famous postulate about the speed of light. We are genuinely building this thing up from first principles.
The big difference here is that we are ditching the whole idea of transformations. Instead of starting with these big postulates about light and space-time, our entire proof is going to rest on just three things we know are absolutely unbreakable: the laws of conservation for energy, mass, and momentum.
Okay, so to test all this out, we're going to use a super simple thought experiment, just a collision between two particles, and we'll watch it from two different points of view.
Here's the setup. You've got two particles, P1 and P2, and they're heading right for each other. They're going to smack together and form one new particle, P. We'll watch this whole thing unfold from the perspective of a stationary observer, O, and then again from a second observer, O1, who's actually moving along with particle P1. That's it. This simple little crash is all we need.
So before we jump into the deep end, let's do a little warm-up. We're going to apply our method to a simple, low-speed collision. The kind of stuff Newton would be comfortable with, just to make sure our logic holds water.
From our main observer's point of view, this is pretty straightforward. The total mass you start with is the total mass you end with, so m0 is just m1 plus m2. Easy. And since the final particle, P, is just sitting there, not moving, it means the momentum of the two incoming particles had to perfectly cancel each other out. So total momentum is 0.
And here is where it gets cool. We take those simple equations from our first observer and we see how they look from our second observer's point of view. And after just a couple of quick substitutions, boom, we get the classic answer we all learned in school. The combined velocity is just v1 plus v2. It works. The method is solid. Okay, now for the main event. We're going to use the exact same logic, the exact same method, but this time we're swapping out the simple classical formulas for the more precise, more powerful relativistic ones for energy and momentum. The core ideas are exactly the same. We are still just using conservation of energy and momentum. But this time, we're using the full-on relativistic versions. These account for things like invariant mass, which is just a fancy way of saying an object's mass when it's sitting still, and how all that energy and mass are related at any speed.
All right, now check out this move. It's really clever. By combining our energy and momentum equations, we can do a bit of algebraic magic to get a new expression for the mass of that final particle, m0. This is a huge step because it gives us this powerful little formula that connects the final particle back to one of the originals. Trust me, we're going to need this in just a minute.
Now let's switch over to our second observer, O1, and see what they see. From their point of view, the momentum of particle P2 before the collision has to be perfectly equal to the momentum of the new particle P after the collision. The scales have to balance.
And here it is. This is the key move. We take that expression for the mass m0 that we just figured out, and we plug it right into our momentum equation. And just like that, the invariant mass terms completely cancel out on both sides. All we're left with is an equation that's all about velocities. It's beautiful. Okay, to get this thing cleaned up and to get rid of those pesky square roots, we have to do something that, well, looks a little messy at first. We're going to square both sides of the equation. Yeah, it's going to explode into a whole bunch of terms, but you got to trust the process. This is the only way to simplify things.
And this is the payoff. After we move all those terms around, all that algebraic noise just collapses. It turns out both sides of the equation were perfect squares all along. And what it reveals is this incredibly elegant and very, very familiar relationship.
So after all of that math, we've finally made it to the top of the mountain. And the view from up here might just change the way you think about physics.
And there it is. We did it. We derived Einstein's exact formula. You can see the classical part, our old friend v1 plus v2, sitting right there in the numerator. But that denominator, that relativistic break that just emerged, it came right out of the conservation laws. It's the universe's own built-in speed limit.
So here's the really mind-blowing part. The method we used never changed. Whether we were looking at slow speeds or literally any speed, the fundamental logic was exactly the same. All we did was upgrade the precision of the conservation laws we started with.
This proves it. There are two paths to get to this same incredible truth. The traditional path requires you to accept these special postulates about light and the very fabric of space-time. But the path we just walked, it only required us to trust the most fundamental, most unbreakable laws of the universe. And you don't have to take my word for it. The authors say it themselves. This shows that the secrets of relativity aren't just contained in Einstein's postulates. No, they are baked right into the bedrock laws of conservation that physicists have trusted for centuries.
And that leaves us with one last big question. If a rule as profound and strange as relativistic velocity addition was hiding in plain sight inside these basic conservation laws this whole time, what other fundamental truths about our universe have we been missing, simply because we haven't looked closely enough at the first principles?